Hello everybody, welcome back for a new chapter in this series on quantum mechanics. And once again, we are going to follow very closely the book from John Townsend, The Modern Approach to Quantum Mechanics, and we will follow chapter 8. I'm going to provide you an overview of path integrals and give you basically the main result from the path integral formalism, and it's very much interesting in the sense that it connects further the classical physics as you would study in, for example, in theoretical mechanics, more classical mechanics, and quantum mechanics, and it will also allow you to understand why electrons do not always behave quantum mechanically, at least from their time evolution. This is the last point that we will bring in this screencast. So remember, in the previous chapter, we saw that we introduced the Hamiltonian, so the operator H, as that operator that's time evolution operator. Actually, that was the time evolution operator is the exponential that's written in the blue equation on the screen. H was in fact the Hamiltonian, but also introduced as the generator of time translations. So the form that we have here is simply saying that we have an evolution from t0 to t prime. As you know, this exponential, again, this exponential of an operator is really only defined through its Taylor series, and we will see that again in this chapter. But so far we have looked at this as the generator of time translations, and in the 40s, Richard Feynman he was more interested in the quantum dynamics, and it, of course, did a lot made a lot of contribution to the field. And in particular, he connected quantum mechanics with the Lagrangian approach, just like you did in theoretical mechanics, where you have those two equivalent frameworks between Lagrangian and Hamiltonian. And in fact, path integral, all this formalism is related to this dualism between Lagrangian and Hamiltonian. So just as in theoretical mechanics, that allows you to understand things from a different perspective and sometimes see different effect. So it turns out for what we do in an introductory courses like quantum mechanics at the undergraduate level, we do not make a big use of path integral. This is a reason why this chapter stands a little bit out compared to the other chapters of the book. We do not use it in practice because it brings difficulties that are not necessary for most of the problem we look at. However, in some specific context, this formalism is actually the only formalism that you can use in terms of dynamics, quantum dynamics. So what I'm going to try to do in this chapter is to introduce you with the idea and what it really means. In particular, I'm going to derive an equation that will be in fact, the single most important result from this chapter, and I'm going to try to make you understand a little bit intuitively what this equation means. It's a complicated equation, but we are going to try to introduce each piece separately and carefully and illustrate it for a couple of examples as well. Okay, so it's time to start. Basically, everything comes back from the idea of what we've already done in the double slit experiment. We often represent the double slit experiment as this idea that there is a duality between waves, I mean, like light, that we can find in light, for example, and particles, right? This is the idea of the double slit experiment, that even though you use one single electron at a time, this electron can diffract through the double slit and then form an interference pattern. And we insisted a lot on the fact that this interference was not an interference between different electrons. That was the interference due to the fact we didn't know which slit the electron went through. And in fact, it's based off the fact that it goes through both of them at the same time. So this idea of the double slit experiment is that we have two paths that the electron can take and will take to create an interference pattern. So we found that in order to understand this experiment, we could understand it fairly simply, I would say, by adding the amplitudes, the probability amplitudes. So let me remind you, of course, that the amplitudes are very different from the intensity. So the amplitudes are usually a bracket, while the probability are the square modulus of the bracket. So the interference comes from the fact that we take the square modulus after adding the amplitudes. And of course, because of the different phases between the different paths, we have interference that's either constructive or destructive. So that shows that there is something out there about adding phases and amplitude of different paths. This is kind of the idea behind the double slit experiment. We have not looked at it that way so far, but this is what the path integral formalism is all about. So that the advantage of this, of course, is that we should be able to, the advantage of this formalism of path integral is that we should be able to look at more complicated experiment like triple slit experiment or even a multiple slit, multiple screen like shown in the bottom schematics. So the idea now is that if we can assign an amplitude, which is a complex number, to each path, we can get the final intensity by adding those amplitudes and take the square modulus. So this is basically the idea. And this idea, of course, is what we've seen so far in all the chapters that we looked at. And what we are going to do now in this screencast is kind of formalize this a little bit and understand what it's all about, really. So for that, I'm going to look into transition amplitude. And again, just for the ease of following the screencast, I always use the same numbers as you can find in the book, of course. So that would be section 8.2. So basically, we are looking at time evolution here. And the time evolution we are interested in is written in this bracket, which should be no surprise to you or no mystery to you. This bracket can be read in plain English as the probability of finding a particle at x prime at time t prime if we initially had it at x naught at time t naught. So this is a probability amplitude, okay? So what we say is that knowing that information is sufficient to understand the time evolution of any general state, and we are going to see that in a second fairly easily. Okay, so now, of course, we already know how the time evolves. In particular, if we have a Hamiltonian that's time independent, we can write the time evolution operator u as the complex exponential, as we have seen a number of times. Just like to point out that so far we have always supposed that we started at time t equals 0. Here we start at time t equal t0. It makes not much difference, but this is don't be confused by this. It's just what matters really is the time interval is between t0 and t prime. So of course, what shows in the exponential is t prime minus t0. So we see here now that we already changed the problem slightly, where we have a bra x prime and a ket x naught. Let's try to move a little bit further with this. So let's look at the general state, and let's have a look at those three equations here. Let's not read too quickly. We are going to look at each equation separately. First of all, let's have a look at the left-hand side of this equation. The left-hand side is simply saying that we are looking at the x prime representation of the state psi at time t prime. In other words, we are looking at the wave function at time t prime at position x prime. That's the usual notation we have on the left. The general state being, of course, psi. Now, the first equality there is simply saying that we can find the state psi of t prime at a later time, at the time t naught, by the application of the time evolution operator. So that's what we have here in red. This is the time evolution operator, just as we discussed a number of times already in this screencast. And we use a usual trick, of course, because what we are doing now, we are kind of stuck But remember that we were talking about bringing an x, what happens at the initial time and initial point that we are looking at. So the way to introduce a new variable is usually to provide a resolution of the identity, which is obtained from the completeness relationship. So we are using x naught, so this continuous basis in one dimension, which is obviously complete. So we can use this expression that's the identity, and we can stick it in inside the bracket. Okay. Now, what's nice about this, of course, is that the bra and the cats do not remember where they come from, and so that brings us to the third equation, where what I mean come from is that we brought a cat bra on the second line, but the next line we can just take the bra x naught to the right and the cat to the left. It doesn't matter. The point is that we can write this now, and the additional step we did is to now apply the time evolution operator to the left, okay, to x prime, and that means that now we have x prime at t prime, okay. So basically we have basically done everything we needed to do, and we end up with this by evolving back in time, and we end up with this fairly simple equation, in fact, that gives you the wave function at x prime and time t prime as a function of the wave function that was at x naught time t naught, and we have to do some sort of convolution over the path. And so this the bracket that we have here in yellow is called a propagator. So this propagator is what I introduced in the previous slide. It's basically the probability amplitude of finding a particle at time t prime at position x prime if it started at time t naught at position x naught. So that's just to show you that if we know this propagator for each positions, then we are able to find the time evolution of the state. So basically, we go back to knowing this bracket is what matters the most. So before I keep going with the formalism, I'd like to show you an example with a free particle. So for a free particle, of course, in one dimension, the Hamiltonian is written just as a kinetic energy with px squared over 2m. There's no potential, it's a free particle. And I can go back to trying to understand this equation here. Again, this is the bracket that we are going to look at. We are going to call it d amplitude. It's the amplitude we're interested in. And once again, we can then now, again, write things in the basis of the momentum. So we are going to again get the identity from completeness relation of the basis p. We can do that, and of course the exponential that we introduced there is just an exponential that's what I call minus I h over h bar times time in the previous slides, but now since the Hamiltonian is just simply given by the Hamiltonian in purple on the left, things are much simpler. In fact, this is the Hamiltonian right there. Okay, so that allows me to, of course, do things very simply because I know that the state P, so the ket P is an eigenstate of Px, and therefore we can more easily evaluate the complex exponential as we've discussed a number of times in this course already. Okay, so what's nice is that we can go to the next line of this equation, and this next line now is a big improvement from the previous line because we no longer have an operator. Instead, we have right here we have a number, okay, because of p being an eigenvector of the operator px. So I can write here as a function of the eigenvalue. Notations are important. As you remember, the hat here is a big deal. It doesn't look like much, but the hat on the operator, that makes this mathematical object much more complicated than this number p, which is an eigenvalue of px. Okay, so on the left-hand side, of course, I get a xp and I get a px naught. So I get all those numbers. And of course, if you remember from previous lectures, we've discussed so chapter 6, we discussed what was the x representation of a momentum state, which is simply given by a plane wave. And so that means that I can directly find what are those brackets. And when I do that, I end up with this equation. Nothing really crazy. I mean, this term here has just come from the from the plane wave coming from here, and this term comes from the Hamiltonian, a time evolution. Now, what's nice about this equation is that it's really integral that's known. There is an analytical formula for this formula. In fact, it's something related to the Gaussian integration. And if you look at tables, you find very quickly that there is indeed a closed form expression for this propagator of a free particle. Okay, so this is the way things work, and this is a very important result. Is basically the propagator of a free particle is like this. Okay, so when we do that now, we can move and look at the evolution for small times. So now let's try to see. Let's try to go back to the general framework, still in one dimension, and see if we can understand what's happening when we have small time intervals. That will allow us to bring a number of new features to understand a little bit this path integral business. Okay, so we are going to suppose still that we want to go from t prime to t0, or in fact from t0 to t prime would be the right thing, but we want to do this in very small interval. And again, we're doing this so that we are going to take the limit of those small time intervals and get back to kind of a dt like we do in calculus. So the time interval will be given by t prime minus t naught divided by n, and will go to infinite at the limit of infinite numbers. So of course we go back to what we know best, which is Taylor series, and that will allow us to develop the complex exponential. That's the time evolution operator. We can write it in first order the way it's written on the screen, with all the terms that we are missing of order delta t square and higher order. We need to do this instead of just going back to the definition of the Hamiltonian as we brought it as a generator, simply because delta t is a finite time. It's not an infinitesimally time at this point. Okay, so we do it this way, and of course the exponential is going to become just a 1 minus I over h bar Hamiltonian times delta t for each interval of time. Okay. Now we have those equations, of course. Again, lots of notations and symbols, but nothing really complicated. On the left-hand side, we are evolving for small time delta t between two position x and x prime. This is a formal way to write it. The first equation on the right is simply a substitution from the Taylor series. And then we are going to suppose that the Hamiltonian can be written as the kinetic energy plus a potential energy, just like it's written there. So nothing really crazy with this equation. Let's have a look now. This is the same equation as I had on the previous slide, but we are going to try to see if we can simplify a little bit. Of course, there are a couple of simplifications we can make. The first one is we know that if we have a function of an operator, when we use that function, we apply it. So a function of an operator is, of course, an operator itself. But if we apply that operator to an eigenvector of the operator, we just have the function of the eigenvalue. That's what's written on the right there, vxx equal vxx. Okay. And at the same time, we know px, so the linear momentum operator is Hermitian, so it can act to the right or to the left with the same eigenvalue p. Okay, so we can do that. That's going to simplify our life a little bit. Again, nothing crazy in terms of the equation, and I invite you to do them on a piece of paper. But what I've done there is two things. The first thing is that to replace v of the operator x by v of the number x, for the reason that's already provided a second ago. And at the same time, we introduce one more time the completeness relationship for the linear momentum. And we introduced it simply because we wanted to be able to apply p of x. And so p of x being the operator. And by doing that, we could replace p of x by a number, p. That's important to do so that we are very careful about what we are doing. So do not skip any steps. We can't mix operators and numbers too easily. So make sure to know what they operate on. Okay. Now, of course, what you see is that it's the usual trick, right? If we look at what's happening in the curly braces here, it looks like the two first terms of the Taylor series of the exponential again. So we can go now backward and replace, okay, just before we do that, I'm sorry. We can write this p squared over 2m plus vx as the energy, like more classically, I would say, no operators here. And one more time, these terms that we have within the square bracket now looks like, those terms look like the first two terms of the exponential, of the Taylor series of the exponential, and of course we have still the remaining O of delta t squared there. So that allowed me to write this equation with an exponential here. Okay, this becomes an exponential, and remember, this exponential is a number. Okay, so it can come out of the bracket, and then we end up with again two brackets that we know well, which is just the x prime representation of p and the complex conjugate of the x representation of p, which we know as being plane waves. So the solution for this, for small time evolution, is given by this term, which one more time is simply a integral of 2 exponential. I mean, simply, it's not that simple because we don't know the value of the energy, but this is what we get. This is a very important equation, so I repeat it on this slide, and I repeat it in blue. That shows it's important. There's a much more important equation we'll see later, so I'm reserving the red color for that one. But that's going to give me the information for small time evolution, so a small delta time delta t evolution. And now, of course, the next thing that we want to do is to see what happens when I look at the evolution from a time t0 to a time t prime. And I'm going to do that by small path integral. And I already know how to deal with each little interval, since that's what I did in the previous section. Okay? So basically what we do is time evolution means that we evolve from the time delta t followed by a time delta t and so on and so forth, unless I get to the time t prime. So in other words, mathematically, this is written from the equation on the top, simply means that I'm going to evolve time t by evolving n times by a time delta t by construction, I would say, because delta t was such that when applying n times, we got the full time between t prime and t naught. Okay, so that's very nice. Why is it very nice? Well, it's very nice because the blue equation that I had, I introduced to you a couple of minutes ago, this is exactly what we have in the exponential. Okay, the exponential, each of exponential is a small time evolution. So now this is the important equation, and it's a bit small because it's long, but what we do is that we are going to stick in a complex, we're going to stick in a completeness relation in position space between each exponential, okay? So this is something now that you should get used to introduce this completeness relation. Completeness relationship really means that we introduce the identity, okay? So we introduce that, and we end up with a number of brackets or matrix elements, if you want, of the time evolution for a small time delta t. And we have as many of those as we have positions. Now you can ask yourself, okay, what are all those positions now, x1, x2, and x minus 1? Well, all those positions are in fact the position that the particle take from a time t, time tn, ti, to a time ti plus 1. So this is the evolution of the position of the particle for a small interval delta t. So you see how difficult this is going to become, because if we bring delta t to 0, in other words, if we bring n to infinity, we are going to have an infinite number of those integrals. So we do understand this is complicated. This is not the point. This is a purely formal, but this is going to allow us to develop equations that will help us understand. So what we usually read those equations, just like very often in quantum mechanics, from the right to the left. And to the right, for example, the first term will tell me, how do I get from x0 to x1? How do I get from x1 to x2? So we are basically jumping from position to position. Now, there is one thing that you have to realize, and this is where you have to stop and think for a second, is that we have integrals in front. So really what we are looking at is to get, how do we get from 0 to all the possible x1? And then we go from x1 to all the possible x1 to all the possible x2. So I'd just like you to realize this, and we are going to illustrate this for a very simple problem, but we are really trying to evolve the particle from all the possible paths that go from x0 to xn, x0 being, of course, the origin, and xn being defined as x prime. And you can see that we do not integrate over x0 or xn because these are the two limiting positions that we are looking for. So this is a bit crazy because you can think about a tree that's actually going all over the place and increasing, the number of leaves increase exponentially. But formally this is correct. This is no problem here. So just written in the green box here about what I just told you about the integration about all the possible paths. Okay, that's very nice. Okay, that's very, very nice. The thing is, if I go back to this, and these equations here, again, lots of equations, you have to realize that when now I'm actually also introducing the fact that we could write it with the momentum operator. Okay, just like to go back here. So we had this equation here, but we are also describing the Hamiltonian using the eigenvalues of the momentum operator. Okay, so just like we did in the blue box. So the blue equation is the equation that was already in blue 3 or 4 slides ago. When we did that, we introduced the integral over the momentum so that we could replace the operator px by the number p. Okay, that was actually a big simplification because a number is much easier than an operator. The problem now, though, is that we have to do that for each exponential. Okay, and means that we are going to introduce n other momentum operator that we have to introduce again right here. So that means that we don't have just an infinite number of integral in x, but we also have an infinite number of integral in p's. But we are not going to worry too much about this small difficulty. The point is that this is all very much logical. Okay. Okay, very good. So in some cases, the problem can be solved, like in free particles. In some cases, this is the only approach we can use to understand a little bit how the physics work. So what we are going to go back to is to just concentrate to that kind of Hamiltonian that I have there. So a kinetic energy plus a potential energy. So this is a single particle Hamiltonian, basically. That's what it means. And we already know what the term, the integral over the momentum looks like, right? This is what we've done again in this screencast. I understand this screencast is pretty heavy in mathematics, but you should follow with the books, and you should maybe watch it a number of times, probably more focusing on where we are going conceptually, and then do the math as well at some point. Okay, so the point is we end up with this equation. So basically this is the same equation as I showed you before, but now all the integral over the momentum, we don't have to worry about them anymore because we worked out things so that we worked in the momentum space, and we use the equation in black to make things simpler. Okay, so this is an equation that's already in red. This is not the most important red equation. Okay, there's going to be a more important red equation, but we are getting pretty close. Okay, we are getting pretty close. For maybe for people who remember a little bit of theoretical mechanics, you probably see in the red on the right hand side the terms in square there. It's really if n goes to infinity, the distance between xi and xi minus 1 is delta x. So delta x over delta t sounds to me like a velocity square. So we would have a velocity square times m over 2, so it's a kinetic energy, and you have minus the potential. That sounds awfully like very much like a Lagrangian already. Okay, so in fact that's exactly what this is. And in fact, that equation, that piece of the equation, and this is what I focus on in the blue box, this is nothing else than the integral of the Lagrangian between t0 and t prime. This is exactly what this is. Okay, so at least the limit, the limiting part. So this is really what this is. So this is how the Lagrangian gets introduced in this formalism of time evolution. So we are getting really close to where we want to be. Okay. So of course the Lagrangian is defined this way, the usual way that you've done before. Now there is a second part in this red equation. It's on the left-hand side, and this is a very important thing to discuss. And this is the second part of this formula. This part in blue, we usually define it as written in the black equation. And that equation really means that we are looking at every single possible path from x0 and x prime. Remember, we are integrating over all those x's. Try to think about this as a tree, all the possible branches that can bring you from x prime to x naught. You can't skip any of them. So there are as many as possible. There is nothing that tells you that one is better than the other so far. So you have to consider every single path. Of course, it's impossible to enumerate them. But the point is, just to simplify the notation, we mean that's what in the blue box here in this case is representing every single path from x0 to x prime. So we are going to introduce the notation that's with the black equation there, and that means simply that we are looking at every single path. Now, if we put everything back together that we've done, we get to the most important equation of this entire screencast, which is right here, which is the red equation, means that the probability amplitude of finding a particle at x prime t prime, if it started at x0 at time t0, is given by this integral over all the paths. Okay, all the paths means really all the paths, all of them geometrically that you could calculate. This is called a functional integral, and it's a functional integral because it's an integral that depends on the function being x of t being the actual trajectory. So the trajectory, again, we don't know what it is. It can be any single trajectory. I've already said that a number of times, but I want to make sure you understand that the function d, that's on the left, that's on the left of this, close to the integral sign, really means that all the possible paths. Remember the definition. And of course, S is the action. Just the same way we define it in classical physics, the action is simply the integral of the Laplacian, and it's defined for given trajectory again. So that's the reason why we have a trajectory. For people who are interested in functionals, and we don't talk too much about function in this course, but we usually use a square bracket. The square bracket usually means that we are talking of function. A functional is a function of a function, so we use a square bracket to show what function we are using. Okay, so this is the action that we do. So the question now is, how do we interpret this equation? And this is where the interesting thing comes in this screencast, in my opinion. So first of all, we consider each path. Okay, I already said that, but this is very important to wrap your head around this. And now what's interesting is that each path, so we sum, so the integral is really what it means. We are summing, we are considering each path. And each path contributes exactly a phase factor e to the power is over h bar, s being the action. So one thing that's really weird at first is that the modulus of the contribution of each path is the same. It's 1, right? It's the modulus of e is over h bar is 1. But it's really surprising. I mean, it's not surprising. We're going to explain it, but it could be surprising because remember that we are considering each path, even crazy path, Nope. I mean, when I say crazy, it means that it's any function, any possible path ever. Okay? So that's how we define D. And so we add all the contribution for each path. And quantum mechanically, that's really what's happening. To go from point x naught at time t naught, to go from there to point x prime at time t prime, you have to consider every single path possible. Okay? And you have to consider every single path, and each path contributes the amplitude with a phase I s over h bar. Okay? So we adding this amplitude to get a full amplitude, probability amplitude. Now, of course, the question is, why do some particles follow the path of least action? So that's really the question, is why do some particles follow the path of least action? So far we know from classical physics that the path of least action is the one that's going to be followed classically. So far we have no indication that would be the case. In fact, we will see that things are slightly different in quantum mechanics. But again, we hope that there will be a handshaking for a macroscopic particle to follow what we expect from what we learn from classical mechanics. So in other words, that a macroscopic particle should follow the path of least action. So how can we reconcile this? So in the remainder of this screencast, we are going to discuss this first by focusing on a macroscopic object, and then after that we will see how this is different for a microscopic object such an electron. So let's go back to the equation that we have developed. This equation is really what we have worked on mathematically to get to this point. This equation looks fairly simple now in this form, but remember what's in it, right? The D function really represent, the D functional, should I say, really represent all the possible paths that can reach from point, that can extend from point x naught and x prime. I insist, this is every single possible path you can imagine and beyond, okay? So remember all the integrals that you had over the x values, all the intervals that we had. But what matters, the way we wrote this here, is that each path that we can find, and this is shown again by the functional d, contribute one phase factor, e to the power I, the action divided by h bar, okay? So, all right, first of all, each path has the same contribution. And the difference between two paths is just the phase. It's just the phase that you get from it. So how can we understand this? How can we understand this for macroscopic particle? In other words, what's the mechanism that makes some paths count more than others? Okay, so we are going to understand that we can use, in fact, this equation to understand why a macroscopic particle will follow the path of least action. That's what we are going to do now in this illustrative example. And the illustrative example will be, we are going to take a particle of mass m, and we will choose a numerical value later, and it starts from the origin at time t equals 0. So the question is, what's the amplitude for this particle to be found at x prime at time t prime? So in other words, what we are interested in knowing is this bracket that I wrote on the bottom right of this slide. Again, this is the probability of finding a particle that started at time t equals 0 at x equals 0 to find it at time t equals t prime at position x prime. This is what the bracket means. This is how we introduced it at the very beginning of this course. Okay, so first of all, there are infinite number of possible paths. The question is, which one will be taken? Okay, so here in this graph, I just plotted the 2 points, 0, 0, and x prime, t prime, and I'm going to plot 3 different paths. And again, remember, there's an infinite of them. This is one possible path, this is another path, and there is a straight line. Of course, as you know, if we are looking at a free particle, as we are going to do now, because free particle is, at least this is simplest Hamiltonian, a free particle will correspond classically to a straight line, of course, because there is no reason to have a deflection since there is no acceleration to it. Okay, so we know that in principle the dotted line on this graph should be the one that the classical particle will follow. Let's see if the path integral formalism can explain that. So first of all, let's consider that path. And remember that in all the equations we had, especially the red equation, as I called it, the one that's important, we had two functionals in there. The functionals are function of a function. This is kind of a shorthand way to say it. So we need a function, and the function we are talking about is x of t. So it's basically the trajectory. Trajectory is a function of time. So the one function, which is a straight line, is given by the equation there in the red box. And this is, of course, the straight line. And of course, we know that this is exactly the solution that we know to be the classical uh, trajectory that the free particle would take. Okay, we know that this is Newton's law. This is physics 101. Okay, so let's try to see a little bit. Let's try to do some calculation now. So as you know, the Lagrangian for a free particle is just the kinetic energy, which is, of course, can be calculated exactly for this particular trajectory that I provided in the red box. And so we can calculate it this way. So remember, x prime and t prime are parameters. They are the ending point of the trajectory. We can calculate the action. The action will be the integral of the Lagrangian between time t equals 0 and t prime. So it's going to be obtained by this. So reminding you that the square brackets are there to denote a functional, so it depends on the function. And we can calculate, of course, this integral. It's actually fairly easy, and we obtain the action of a free particle. Nothing really difficult. Now, if we consider a small object, let's say a microscopic object of a mass of 1 gram, of a distance of 1 centimeter for a time of 1 second, so typically small object that being thrown, taking 1 centimeter in 1 second, we can calculate actually the number. We can calculate this action, and we find that the action divided by h bar is going to be that huge number, 10 to the power 27th radian divided by 2. Okay, so this is a huge action, and that means that this is the phase, if you will, that's going to enter into the equation that we are working with. Okay, so that's one thing that we get. Okay, this is just a single number. Now let's imagine that the trajectory, a possible trajectory is a parabola, and the parabola, of course, will not be the trajectory that's followed by a free particle, but this is one of those trajectory that we should consider when we calculate the entire probability, all the probability amplitude, as we discussed a few minutes ago. So we have this trajectory, and we can do the same exercise. We know already that that trajectory should not be the classical one. Okay, so we know that if you if you do experiment, you will never find a macroscopic object moving along the green line if you don't have a potential. Okay, that's clear. So the Lagrangian, of course, can be calculated fairly easily from the equation. The action similarly can be calculated in an elementary fashion. And of course, we can calculate can get a numerical value for this. And the numerical value we get is 2/3 10 to the power 27 radians. So if you compare to what we had on the previous slide for the classical trajectory, we found that we have 1/2 10 to the power 27. So already we see that what's interesting is that the the um, the action is lower for the particle that for the trajectory that's classical, which is a good thing because we know that of course classically this is true. But really, this is not exactly the most important thing in our perspective. In our perspective is the fact is that what matters is not the actual value, is the fact that we have to follow the least action. Okay, so it has to be at the place where the action is minimal. And we are going to see, and it's very important that it's minimal. it's very important that it's an extremum, not an inflection point, or not a maximum, but the minimum. And we are going to see that now. And I think that is the example as described in the textbook is extremely enlightening, and this is what I'm going to do now. In fact, it's not super complicated. So the question is, why does a macroscopic particle follow the straight line, or does not deviate from the straight line, and does not go through a parabola like this? That's the question. Well, the best way to do this is kind of a habit we do when we work with functionals. We are actually bringing a parameter to modify a function and to see the behavior of the functional for that family of function. So in particular, let's have a look around the classical trajectory. And for that, we introduce a new trajectory, a new parameterization of a trajectory, which is very similar to the straight line, but with a slight deviation from the straight line. That's going to, and the intensity of that deviation is going to be given by a parameter epsilon. Now, of course, if you check that trajectory indeed connect the point 0 and the point x prime at time equal t prime. So we are good. So we really have one of those lines, those curves that connect the two endpoints as we want. Okay, the endpoints obviously never change. We can calculate the action. Again, this is the algebra is fairly elementary. I'm not going to go into details. I mean, the equation is right there. But the point is, the most important thing is the result. So you find that the action for that particular trajectory is the classical action we already calculated 2 slides ago, times a correction. So we have 1 plus epsilon squared over 3. Of course, we know that if epsilon equals 0, we get the classical action. We know that. But what's interesting is that we find that indeed, for that family of trajectory, the least action will be for epsilon equals 0, right? Because since we have an epsilon square, we see that any value of epsilon that's not 0 is going to increase the action. So it's very important because that means that there is no linear term. If there were a linear term, taking a negative value would actually bring down the action. And that way, we would see that we are not at the minimum action trajectory. So what's important is that at first order, there is no correction to the action. It's only a second order correction to the action in epsilon. Okay, that's very, very important what I just said. What I just said is that if you were slightly deviating, when I say slightly, is epsilon very tiny. So if you're slightly deviating from the classical trajectory, you would have the action would be essentially the same. In other words, the phase will be the same, and that particular path would actually be the probability of that path would actually be enhanced. So you would have kind of a constructive interference. So mathematically, what it means is this. The change in the action is going to be equal to 0 at first order. And by the way, to get that result, you would need to do a functional derivative. We don't want to go into this in this course. This is not super complicated, but we have to do a functional derivative. And you find, and this is the important result highlighted in red, is that because the delta S, the change in action for change in epsilon is 0 at first order, we find that the phase factor is a constant. So you actually keep adding the same value. So basically, if you keep adding the same phase, this is how you get a constructive addition, just like we saw in the two-slit experiment. So it shows that the classical path seems to be robust, seems to show that every small modification of the trajectory around the classical trajectory is going to reinforce the probability of that classical trajectory. So that's kind of nice. And of course, we know that the reinforcement only comes from the fact that we are at a minimum of the action. It's because we had the least action possible that every correction are second order, because if the corrections were first order, we would not be at a minimum, okay? And this is kind of reminding you that the first derivative, there is no linear term in the harmonic approximation for the spring, for the harmonic oscillator we saw in chapter 5. So in any case, the point is because we at the least action, there is no linear term in the change of the action. There is a second order term. And so that means that the paths are constructively adding. So what about the other trajectory that we looked at? And can we do the same? We can do the same, and in fact, that's what we do on this slide here. Again, the formula that you have on the top left is just a parameterized set of trajectories, but these trajectories are parabolas with a correction to them, and which is a correction of a higher order. And what you know that when epsilon equals 0, we have this parabola, which is not the least action for sure, because we found that its action was 2/3 10 to the power 27, so which is higher than the action for the straight line. Okay, so if you calculate the action for this, and again, this is not a very complicated calculation, but the point is that the action for this particular set of trajectories is not a minimum, and you can see that by the fact that the action changes 1 plus epsilon over 2. It means that if you take a negative epsilon, you're going to reduce the action. Okay? If you get a positive epsilon, you're going to increase the action. Why is that important? Well, it's important because that means that the first order change in the action when we change epsilon is non-zero. If it's non-zero, that means that the total action, so the action plus delta S, the classical action plus delta S, is going to be a number that changes as a function of epsilon. Okay, so this is very interesting, and you will see that this is actually a destructive interference, and that destructive interference make that particular path unlikely. Because by adding all those phases, all those complex exponential, the sum of them becomes on average 0. We are going to see that even better with the idea of phasors. Okay, the phasors is a way to understand this. So this is exactly what I just told you. We have to add the different amplitudes depending on the actions. Okay, so we can actually, of course, these are unitary numbers, right? This is from the Euler relationship for the complex exponential. We see this in the unitary circle. We see that we can see them as vectors that live on the unitary circle if you use the x-axis as the real part and the y-axis as the imaginary part. And we are going to see that in a couple of slides much more easily. So the idea is that adding phases is just like adding those vectors. Okay? So here's what's very interesting about this. Let's go back to this action for the non-preferred path. Okay, so it's a path that we corrected. This was the parabola, and we corrected it with an epsilon term. Okay, so we have this term right here. This is just a repeat of the 2 slides ago. And so what we find is that, remember, this is the phase. This is the term that goes into the phase divided by h bar. So the actual phase is actually given by this. Now, it turns out that if epsilon is chosen so that the term on the left is equal to 2 pi, this is enough for the phasor, for the total phase, to have rotated by 2 pi, by 360 degrees. But remember, S for that particular path and for macroscopic particle is huge, is 10 to the power 27. So any tiny value of epsilon, okay, any small value of epsilon will be sufficient for the phase to change significantly by a value of 2 pi. In other words, the phase for any value of epsilon is going to go all over the place around the unitary circle. And on average, because remember we have to add every single path in the formula that I showed you, so the red formula, on average, that contribution to this contribution to the amplitude would be 0. In other words, that path is not going to be a path that's going to be adopted by the particle. And of course, you can see that by the fact that the phasors are actually going to add to 0. And I'm going to show you a different picture in a second that's maybe a little bit more clear. So the macroscopic value, this happens a very small value of epsilon, and of course, we end up with an addition of all the phasors going to 0. Now, if you go to the classical path, this is a very different story, because for classical paths, there is no first order correction to the action. The action is only corrected to the second order. So you would need a much, much larger value of epsilon, okay, to get a shift that's significant in the phase. So that means that for all the trajectory in the vicinity of the classical trajectory, we have constructive interference, which makes the classical uh, trajectory the most likely to happen. So, in other words, the particle, the macroscopic particle, because of the huge action that corresponds to it, will take the path of least action, for all because of those phasors. So let me show you a slightly different way to do it. You remember that we can represent the phase with a green arrow on the unitary circle here. And of course, all those phasors live on the unitary circle since they are all of magnitude 1. So the angle that the green vector does with respect to the x-axis is, of course, s divided by h bar. And so along a classical path, that angle almost does not change. Remember, at first order, it actually does not change for around the path. So in other words, you have an addition to phasors. So you have they add constructively. And so that means that that system is actually that particular trajectory has a higher likelihood to happen. Now, around the non-classical path, as you know, as I explained to you, the action changes linearly with epsilon. So even for tiny epsilon, because the action is so huge, for a tiny value of epsilon, the phasors is going to rotate like crazy around the circle, around the unitary circle. And on average, because you are summing all those, on average, they're going to sum to zero. In other words, you have a perfect destructive interference, and you will never see this trajectory for a macroscopic object. So that's a very nice, very nice and convincing way to connect quantum mechanics to this trajectory of a macroscopic object. But now let's try to remember we are talking about quantum object. So these do not behave quantum mechanically, even though quantum mechanics can explain what we measure classically. But what about a microscopic object? Let's consider an electron. This is where I'm going to conclude this screencast for the next couple of minutes. The phase difference between the two paths I mentioned to you, okay, the straight line and let's say a parabolic path. The difference in phase between the two can be calculated using the formula I showed you in a few slides ago. And for an electron, where the mass is of course much smaller, the difference in the path will be about 1/6 of a radian. So in other words, the difference between the two paths is going to be very small. Okay, this is going to be very small. So if the difference between the two paths is very small, the two paths are essentially coherent. Okay, so that they are coherent with the classical path. But that means in this case that the electron has a finite probability to live on the two trajectories. In fact, it has many different possibilities for the trajectories compared to the macroscopic object. And this is related to the fact that you would need to go very far away from the classical trajectory for the phase, total phase, to change significantly. And the reason for this is because you have a factor of 1/6 instead of a factor of e to the power 27. So the electron does not behave classically at all, in case you still had not realized since this beginning of this class. So we can actually solve those problems and see really the handshaking and the crossover between quantum mechanics and classical. Now, if you have followed, and I'm sure you have, you could actually ask, but hold on a second. How could we even do the experiment? How could we even have the double slit experiment at all? Because we always use this nice plot here. This nice plot, which arguably is very simple, is based on classical trajectories. Okay? It is based totally on classical trajectories. So why can we do that? I mean, why can't we use this path instead, for example? In principle, this path will be important also in the entire solutions that we were looking for in those famous red equation I spoke about. So why don't other paths contribute, such as the green one? Well, actually, the reason is this. The reason is, again, don't forget that this is done experimentally. Experimentally, what's happening is that, and again, look at this equation there for the classical action. The reason is that experimentally, the electrons that we use for this kind of diffraction have a pretty large kinetic energy. So we are doing a diffraction experiment. That means that the time t prime that the electrons take to, let's say, go over, let's say, half a meter, or 40 centimeters, as I have in this slide, is going to be much smaller. So it's going to be 10 to the power minus 7, for example. It goes very fast from the gun, from the electron gun to the screen. So the time is very small, okay? And so that means that the action, actually, the action of that correspond to an electron at such a high speed, such a high kinetic energy, is actually fairly large. It's like 10 to the power 9. So it's not 10 to the power 27, but it's still a very large action. So that means that when we have very highly energetic electrons like this, they do behave essentially classically until they start to diffract. Okay, and so that's the reason why we use those grading and those holes in the screen um, to create a diffraction pattern. Okay, so the Stern-Gerlach experiment, on which the entire course here is based, where we also treated electrons really classically in terms of trajectory, and probably most students don't even think about that. The reason why we can do that is because the action is very large because of the energy that we use to accelerate the electrons initially from the gun. So of course the phase factor is this again, and S over h bar being very large. We favor the straight and classical lines. So this is because the phase is large, and as I said, only as every small deviations from the classical path will actually make the trajectory unacceptable. So it's time for me to get to the last slide of this presentation. And my summary is going to be very simple. My summary will be just a single equation, and this is what I call the red equation. That equation really is a very loaded equation. There is a lot to unpack. What's important in this equation is that it provides you the probability amplitude to go from one point at a given time to another point at another time. And it's obtained by integrating over all possible paths, and that concept of all possible paths is embedded in the functional D. And each path contributes one phase factor. Okay, this phase factor is obtained from the complex exponential with the action. So the action calculated from the integration of the Lagrangian. And that particular, what's very interesting about this is that the paths that are going to be followed will be the ones that correspond to a constructive interference. That means where those complex exponential add up coherently, in other words, where they have very similar phase. So I think this is a fascinating topic. I only scratched the surface, but I hope that I gave you enough to get the conceptual framework to maybe move further with this and explore more in detail. I thank you very much for your attention.